Ok. Allora, maybe I speak in English even though I don't see anybody uh, different from Italians, but for the recording. Okay, so do you remember that last the end of last lessons we spoke about the easing model, no? As you remember, which is a very simplified model, a standard model of um, of a magnetic material with the spins, which are down or up, or clearly -1 and 1, or even 0 1 if you want, just changing something. So this is the energy, which has a term that depends on the fields. Let's say this one, the fields that the neighboring site generate. So for instance, in this case, it is 0 because we have 2 1s and 2 -1. So the external field, the local field here is 0. While, for instance, for this one, the local field is 1. We have 3 1s and it is 2. We have 3 plus 1 and 1 minus 1. So here it is 2, here it is 0, here it is again 0, here it is again 2, and so on. So these are how we can compute the local field. And then we may have an external field B or H, depending on the terminology. And what we expect is that for a large enough temperature, we have 0 magnetization. Magnetization is just the sum of the spins. While below a certain critical temperature, this is for field B or H equal to 0, we have 2 possible magnetization states. And with respect to the external field, this is the H, this one, or the B. At the critical temperature here, we have this kind of behavior, while here we have a first order phase transition. And okay, this is essentially the phenomenology we expect. We can use Monte Carlo simulations in order to generate the simulation. This is the result of one simulation. So in the red one is the magnetization curve. So this is the critical temperature. Actually, this is J over T. And so we can either speak of a critical temperature or a critical value of J, fixed temperature, or a critical ratio J over T, which is about 0.44 or 44 or 42, I don't remember, which is essentially here. And if we measure also the variance of the magnetization, we see a clear divergence of this variance at the critical temperature, or the critical coupling, because here we have essentially the appearance of all kinds of clusters. And we shall see in a moment the pictures of this. And we can also formulate an approximation of a mean field. Assuming that the system is homogeneous, then if I have a certain probability m, which is the magnetization of having, so this is the number of plus minus the number of minus divided by the total number of clusters. So this is essentially also proportional to the probability of having a plus site. So the local field can be approximated by the number of neighbors time their magnetization, and so we can essentially write down the expectation value of the magnetization, and this gives a self-consistent equation that can be solved, say, graphically or numerically by finding the intersection of the diagonal with respect to this hyperbolic tangent. And so for large t, essentially we have only the 0 point. For a critical temperature, we have tangency, so we have large fluctuations because here there are many solutions essentially. Two, no, three actually, mathematically, but it means that a lot of different values of m are compatible. While for small enough t, we have two intersections, and so again we recover this bifurcation diagram, this phase transition diagram. And we can also try to formulate an extension of the Miller field, which is the let me include also Daniele, and an extension of field, which is the Landau theory. The idea is to develop the free energy with respect to the magnetization, and the idea is that the equilibrium expectation value corresponds to the minimum of the free energy. So the idea is that for large enough temperature, the free energy has this shape, so the minimum is for m equal to 0. This is the critical temperature for which m is free to fluctuate, and this is below the critical temperature where the symmetry is broken, and we have either a positive or a negative magnetization. This can be reproduced assuming that the free energy has a shape like this. That we shall see also is the starting point for a more sophisticated formulation. And clearly, if we also have an external magnetic field, the symmetry is broken by this magnetic field. So essentially, we have the probability of having a certain value of magnetization is different from that of having the opposite one. And okay, so these are the simulation that we already seen. At performing simulation on a relatively small system, we can actually reconstruct the picture of the free energy. So this is the probability distribution for a system of, say, I don't remember, 20 by 20. And if you take the logarithm here, this is simply because the probability is here 0, so I have to put a certain value of the logarithm. But you can see that we have essentially the shape suggested by Landau, while for this is for t greater than tc, while for t less than tc, we have the possibility of observing plus and minus magnetization. In order to observe both in the single simulation, I have to use small lattices, otherwise the transition is not apparent. I could repeat several simulations. And if you take the logarithm of this, you see actually the shape that was forecasted by Landau. So the idea is holding. And we can also do the same, for instance, for the Domani-Hinzel model, where we do not have energy, we do not have temperature, we only have probabilities. But if we plot the logarithm of the probability distribution, again, and for, you see, for P very near PC, because in the Domani-Hinzel we have an absorbing state. So if we are sufficiently below PC, the system falls into the absorbing state and we don't see anything. But you can see that this is the absorbing state, so it has a well to minus infinity here. It has so a certain probability of observing a finite density. In this case, it is not the magnetization, is the number of ones. And there is for P below PC, there is always a possibility of going into the absorbing state for finite system. But when we increase the probability, and clearly if we increase also the size of the lattice, we see that both the free energy barrier grows, and also there is a kind of entropic barrier that increases because the equilibrium point goes to larger values of C, and this means that to have to go into the absorbing state, you need to say to perform a random walk because each movement is random in the simulation, and overcome this barrier. And remember that we draw this picture in one dimension using the aggregate magnetization density, but for a given value of the density, there are a lot of say that see, I can put here this. For a given value of the density means that the number of ones with respect to the number of zeros, I have a lot of configurations that can have this magnetization, which is given essentially by the binomial term of the sides of the system with respect to the number of ones. So this is L factorial divided by CL factorial and L minus CL factorial. And this clearly drives the system towards a magnetization order 0.5. So essentially, in order to go to have to accumulate these steps in order to go into the absorbing state, we have not only to go against the free energy, but also against the entropy, which drives the system towards 0.5. So this is essentially the reason for which we can observe a phase transition, even though there is always a small probability of going into the absorbing state. Okay, so we now, this is for just for a recap, for making a recap of what we did in the last lesson. And now let me go to the beginning. We would like to explore other aspects of the system. So, for instance, to extend the idea of mean field that we have formulated for the easy model, so for equilibrium model, to general phenomenological model. I mean, phenomenological means that it is defined by a Markov process. So where we do not have the concept of energy or of say equilibrium and so detailed balance and so on. So the idea is that we start from this Markov process, as we already have seen, and where now we assume that the Markov process is given by a local process, like for instance in the Domani-Kinsel model. So the probability of going from one configuration Y to another configuration X is the probability of having all local transitions. So for instance, Y is 1, 0, 0, 1, 1, 0. X is say 0, 0, 1, 0, 1, 0. So in order to observe given Y in the configuration X, I have to, the probability is computed by taking the probability of going from 1, 0 into 0, the probability of times the probability of going from 0, 0 into 0, times the probability of going from 0, 1 into 1, etc., etc., etc. This. And so we can write, technically, we need to also to insert periodic boundary conditions, so we have to extend the configuration y to y tilde. But this is just a technical detail, not very important. And clearly, we have to sum over all possible configuration in order to find x. And this is why this Markov equation, which is very nice, but it is difficult to compute because for reasonably large L, say order 10, we already have a million term just in W, because to the L, this P is the size to the L. So for L equal 10, it is 1,000. For L equal to 20, we have 2,000, 1 million. And but now what we can do is, first of all, to write down explicitly all the terms. Now, this, I have put in this distribution the subscript n, meaning that this is a distribution that depends on n plus 1 terms. This depends on n terms. But the idea of a probability distribution is that if I sum over one of these terms, I get the reduced distribution of with an index n minus 1. Clearly, I normally sum over the first or the last term. And while these are conditional probability, and the idea of a conditional probability is that if I sum over x, I get 1, not if I sum over other terms. And so let's start from this one, summing over the last term. No, this one, this. If I sum over the last term, which appears, no, first of all, if I sum over the last term of this one, this that appears only this, you see that using this condition, this means that this last tau goes away. Now, the last term of this other side, which is this one, only appears here. So I can sum over this, getting the reduced distribution. So summing first over xn, then on yn plus 1, I can have, making no approximation, I can have this relation between now n minus 1 and n. So I can continue up to the end, and the last term is this one. So exactly without an approximation, I can say that the probability of observing just a single site depends on the combined probability of observing two sites. This is in equilibrium, so I can drop the time index, and times clearly the transition probability. But clearly this is given by another equation, which gives a probability of observing a pair giving a triple, and so on. And this is exactly equal to the original Markov equation, and sometimes it is called I don't remember, the Bogoliubov, I don't remember, hierarchy, which says that essentially that also in the Liouville approximation of dynamical system or in a stochastic system, we can formulate either the Markov equation or this chain of equations. Now, the idea is to truncate this recursion at a certain level. The simplest approximation is just to factorize the probability. This means that I assume that the joint probability of observing a pair of sites, say 1, 0, 0, 1, 0, 0, etc., etc., is just the product of the probability of observing the single sites. This is true if I take a configuration at each time I reshuffle so that, I don't know, I have the same configuration with the same number of ones and zero, but completely shuffled. And otherwise, clearly, normally there are correlations among spins, and these correlations normally diverge near the phase transition. So we can already expect that this approximation can be good far from the phase transition and very bad near the phase transition. In this way, we can close the hierarchy, and we can find the just a closed equation for P1, and since P1 of 1 plus P1 of 0 is equal to 1, I have just one variable. I may call C equal to P1, and we can get this for a system like the Domani-Kinsel model, something like this. For instance, if we now put this equal to 0, so this I can throw away. These two are equal, so they are 2p, and this is q. We see that we get this equation, which is now a dynamical system. No more probabilities and no more random numbers. And so we would like to find the fixed point of this equation. You can see quickly that there is in the limit C prime equal to C. So you see that the one solution is C equal to 0, so that we can now simplify the system, and the other solution is C star equal to 1 minus 2p divided by q minus 2p. Now, we can either compute the stability of the system, or say that, okay, phase transition occurs when the two solutions are the same. So, for instance, say, consider one line just to have just one parameter, for instance, this one, or this one, or the bond percolation problem, any line here, say parameterized by the parameter p, you have the solutions. So this is p. The solution C equal to 0, which is always present, while the solution C star, so this is 0, the solution C star appears at a certain value of p, which is 1/2 here. And so what is said by this approximation, this solution, is that the phase transition should occur for p equal 1/2 independently of q. This is the numerical line, so you see that there is a certain difference between the mean field approximation and the actual values, which this difference is due to the correlations inside the system. We can try to improve this. In order to improve this, we can try to not to cut the system here, but for instance here at the following level. Clearly, we have now to express P3 in terms of P2. One possibility, which is called the Bayesian possibility or maximum entropy approximation, is this one. So you see that if now we can check that this is consistent, because if I sum, for instance, over z, I should get, just wait a minute, Samuele, sono a fare lezione, ciao. So if we sum over z, we should have P2 of x and y. And actually, if you sum over Pz, you get P1 over y, which simplifies, and so you have P2 of xy. This is just a necessary condition, but it is one could find other forms of the probability distribution of the extension. For instance, there is another one which is called the minimum entropy extension, which sometimes gives better results. But for the Domani hints, this works quite well. And so you see here the results of the computation. This can still be done by hand. Others need to use a computer in order to perform the computation, because while the first approximation here gives simply one equation, at this level we have 4 terms. We have P00, P10, P01, P11. Clearly, the sum of this gives 1. So 1 can be eliminated. These two can be considered equal, and so we have just one parameter, which is the probability of 1001 and the probability of 11. So still we have two equations now. And clearly, for a higher order approximation, we have an exponential number of components of equations. So we have to use maybe computer. But you see that increasing the level of approximation, we are approximating the experimental curve. Clearly, we have to suffer enough. And we can also check this using our NetLogo. I can show you the I don't remember which one is this. No, let me check. This one. Okay, should be this one. That I can also put in the shell directory. So, okay. So, in this case, I am performing. I have divided the system using the patches in several small squares. This one. In each square, I assign a value of, say, P and Q. Okay. This is Q, and this is P. And each patch is computing a simulation on a vector of length L. So what we are seeing here is not a single simulation, but a lot of simulations, actually about 2,050 and 500 simulations, for different values of P and Q. And if we perform the numerical simulation, we see essentially the density plot of the system after a long time. This is the phase transition that we have already seen, and these are the densities in the active phase. But I can also do the same for the mean field equation. And for the mean field equation, I find here the separation. Oh, this is P, not Q. This is P. For P equal 1/2, you see, here clearly the density is near 0, so we don't see much. But this is essentially the transition from 0 to different from 0. If now I use numeric, but with random shuffling, so every time I reshuffle the system in each simulation, I get again the phase transition for P equal 1/2, like in the mean field. This is just for checking that the mean field approximation is essentially the same as the simulation done with a continuous reshuffling. And this is, if you think, the classical chemical approximation. When you write down the chemical equations, these are mean field equations that are formulated assuming that the reaction is stirred enough so to break any spatial correlation in the system. Now we have seen that the phase transition in statistical mechanics or in Markov process at the mean field level corresponds to bifurcations in the corresponding dynamical systems. We can, for instance, check all this stuff exploring another model which is called the BBR, which is just an extension of the Domani-Kinzel model. In this case, we have three site interaction, so that now we have the configuration 0, 0, 0, 0, 0, 1, 0, 1, 0, and 1, 0, 0, or 0, 1, 1, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So, like in the Domani-Kinzel, we assume that it is a totalistic automata. So we group all these together and all this together. We still have an absorbing state in 0, but we want to have also an absorbing state 1, so to make the system more symmetric. So you can again call the probability of having a 1 if there is just 1 in the neighborhood P, and the probability of having 1 if you have 2 ones in the neighborhood Q. And so again, you have still a phase space with 2 parameters, P and Q. But now, clearly, the phase diagram is different. And in the simulation, you see that now we have two different transitions. This transition here from a quiescent state 0 to an active state. This is density different from 0. And then another phase transition from the active phase to the state 1. And if you cut this transition here, you see this transition, which is very similar to what happens in the Domani-Kinzel model. And this one, which is essentially the same but reversed here. So this is here, and this is here. But in this system appears a new phase here, which in some sense corresponds to the Domani-Kinzel transition just in this point, because in this point when Q is equal to 1, 1, 1 always goes into 1, so we have on this line, we have two absorbing state, and here it always goes to the absorbing state 0, and here it goes on the absorbing state 1. So essentially, the BBR model allows to expand this line into a whole space, and in this space you have again a transition from 0, but now not in active phase, but directly in the phase 1 if you come from this direction, or from 1 into 0 if you are coming from this direction. Clearly, normally the transition is that you start in 0, you stay in 0 until you arrive here, and then suddenly you go to 1, or you go to 1 and you stay in 1 until you arrive here, and suddenly goes to 0. If you want to observe transition which is more actually not, this is what I would like to observe, but actually you are not observing this, because if you start from 0, you always stay in 0 because it is an absorbing state, even though it is unstable. In order to break this stability, we can add a small probability epsilon of going from 0 into 1. So this is 1 minus epsilon, and this is 1 minus epsilon. So the probability, epsilon is the probability of going from 1, 1, 1 to 0, or from 0, 0, 0 to 1, say order 10 to the minus something. Clearly depends on the lattice size. Suppose that it is so small that you have only one, at most one exception for each time step. Then you really, now when the 0 becomes unstable, it can be near 0, because clearly now the density is order epsilon. So, but still you have a transition here from almost 0 to almost 1, and the backward transition here from 1 to 0. And so you observe an hysteresis cycle. And so in this model, you can have both continuous transition and discontinuous transition. Moreover, in this point, we have a transition from a state in which you have two symmetric absorbing state into an active state, for instance, if you go in this direction. And as we shall see, this is in a different universality class, but this is not really important. And clearly, we have symmetry with respect to this line. We can exchange Q and 1 minus P and 0 in ones, and you have still the same system. If you want to perform a mean field, we can do it together. So remember, we have the probability of having 1 given 0, 0, 0 is 0. The probability of having 1 given, say tau, given 0, 0, 1, 0, 1, 0, 1, 0, 0 is P. The probability of having 1 given 0, 1, 1, 1, 0, 1, 1, 1, 0 is Q. And the probability of having 1 given 1, 1, 1 is 1. So, which is the probability of having 1 at the next time step? This is given. This does not contribute. This contributes for 3 times P, and the probability of having 2. So let's assume that we call C, as usual, P of 1. So C prime is given by 3 times P, this parameter, times the probability of serving 2 zeros and 1s. So it is C square, no, C times 1 minus C square, 2 zeros and 1. times 3 times q c square 1 minus c, so this is 1 and this is 0, plus c cube. So again, so this is the mean field equation. As before, the fixed points are the possible asymptotic solution. So you see that there is one solution C equal to 0. If you check, if you bring this from the other side, it becomes C minus 1, so can be written C minus 1 times C plus 1. And so you see that there is another solution C equal to 1. These are the two absorbing states. And finally, you get from the last equation, you get this condition. And again, you can find where these different solutions coincide, and you find that this is for p equal 1/3, it gives 1 and 0, so collides with this for any values of q. And if you put here q equal to 2/3, you see that this becomes 2/3 becomes 2 plus 1. No, this should be minus. So 1 becomes minus 1. So you simplify 3p minus 1 with 3p minus 1. And so you have the collision with this one on this line. And so this is the phase diagram for the mean field approximation of the VBR model. You see that we have actually the transition from the absorbing state to the active and then to the absorbing state 1. And here you have the coexistence of 1 and zeros. So you have a region of, say, discontinuous transitions. And that's all. So you can also, we shall see, extend this kind of model to larger neighborhood. Now, another interesting transition is about what happens to a small defect or disturbance on the system. Clearly, since we are considering a stochastic system, we have to assume that the two replicas, so the one which is evolving and the one which is evolving with a small modification, uses the same random numbers, otherwise clearly they differ. And if you do this and you observe what happens to a small disturbance or to a whole line of disturbance, you can find that in some region, the defect is absorbed in a few steps. In other regions or for other values of parameters, the defect can spread. And if you look what happens in the Domani-Hinzel model, you see that this is the 0 and this is the active state, but not all active states. In not all active states, the damage can spread only in this small region. And you can also extend the model with a different value. This is the probability of having 0, 0 into 1. And what you see is that this plane here is the original Domani-Hinzel plane. So this is the phase transition we have seen. Actually, the chaotic, so the region in which there is a damage spreading is more extended, not only on this plane here, but also in the phase W different from 0. This is because the damage spreading phase has always an absorbing state, the state in which you have 0 defects, 0 difference, and this absorbing state is present on all this cube, not only on this face or on the top face if you exchange zeros and ones. And so you can say have this. Another thing to be careful is that, as we shall see probably both in the following, I don't know, is that since the implementation, for instance, of the Domani hints is, for instance, given written in this way, you write x prime equal to tau, so you extract a random number, you compare it with say some probability p times the configuration x minus XOR x plus. So this means this is a site, the spin at site I. This is I minus 1, and this is I plus 1. They are in the configuration 0, 1, and 1, 0. For instance, a way of identifying these two is to take the XOR, the sum modulus 2 of the two spins, and this is 1 only in these two configurations. Then you have to extract a random number to compare it with P, and if it is less than P, and this is 1, so this is 1. Or, I'm going here, you extract a random number, you compare it with Q, and you have now a condition for which the two spins are ones. So this could be xi minus 1 times xi plus 1. Okay, but now you see that for the single simulation, you can extract the same, use the same random number here, or two different random numbers, and nothing happens. So essentially the simulation is the same. But when you are using two replicas, it makes a difference if you use the same random number or two different random numbers, because if you use two different random numbers, because in the two configuration, in one you can have 1, 0, and in the other you can have 1, 1. For instance, this is the defect, and so in one configuration it's 0 and the other is 1, and so you have in one configuration 1, 0, and the other 1, 1. Now, if you use the same random number, no, in one simulation, in one configuration, this is true with this condition, and in the other with this other condition. And so essentially you are comparing the same random number with P and Q, and they are different if R is between P and Q, or the opposite if Q is greater than P. While if you use two different random numbers, they can be different also. So essentially, if these are the two random numbers, R1 and R2, there is a whole region, no, in which this one is 1 for R1 less than P, say here is P. This one is 1 for R1 less than Q. And so they have different results in these two regions, and not just in a single region like here. And so the results can be different, and actually depending on the correlations between these two random numbers, you have this region if they are the same random numbers, but this can be this active region can extend up to here. Here is when you have two completely uncorrelated random numbers, R1 completely uncorrelated from R2. And clearly there are also intermediate regions. And if you do the same in the BBR model, you remember we had in the mean field we had this. No, this is the mean field. In the mean field we had this region. See? Sono fa lezione. So these are the absorbing 0, the absorbing 1 state. Here is the first order test transition, and here is the damage spreading in the mean field approximation. While for the actual simulation, you have these two transitions here, and these two, and this is the active region. So essentially very similar to in the two situations. And another interesting phase transition is happens if you take a deterministic rule, but you apply this only for a certain number of sites. Otherwise, it stays. It stays the same. So maybe you can write it like this. You take a random number, you compare it with a certain probability or the opposite of this probability, and if this is true, so with probability 1 minus p, you see that you cancel this and you get the actual simulation. If this is false, you actually, I'm not sure that it is the right formulation. I have to check. But the idea is that when you compute your value, you take this or you keep. Actually, I think that here we have a parenthesis missing. So if this is true, you cancel out x and you get the function. If this is false, you throw away this and you stay with the same value. So essentially, it is a dilution of a rule. And clearly, when p is very near to 1, you have essentially the case in which, in most of cases, you apply this f at most to one site only. So it is a classical sequential dynamics. While when p goes to 0, you have the classical parallel dynamics. So you can also think to this asynchronism as a way of passing from an asynchronous to a synchronous dynamics. And what is interesting is that we can have quite a different, for instance, a profile of, say, this is the density of ones, changing p. You can, say, go from a certain value to 0 or vice versa. And I just cite this. I'm passing, but there are some studies about this asynchronous phase transition. And what is interesting is that the simplest mean field approximation completely fails. Let's see. If I write the mean field approximation for this equation, you get something like this. With a probability p, you stay with the same density, and with probability 1 minus p, you apply the mean field. But now, if you are considering the stationary state C prime equal to C, you see that this and this gives you 1 minus P times C. This cancel out, and so you lose completely the P dependency. So it means that the simplest mean field approximation is completely unable to reproduce any of these phase diagram. And if you think that this is something that, for instance, could happen for chemical reactions, very diluted chemical reactions, and so on, it should be so interesting to understand that the simplest mean field approximation can completely fail. And clearly, using other kind of approximation, like for instance the ones that we have seen before approximating the Domani-Kinsel model, can be able to reproduce some of these aspects. And we can also study the damage spreading in different kind of approximation. You see that you have, if you want to formulate, for instance, for the Domani-Kinsel model, here still have to put parentheses. So this is the formulation with two different random numbers. And since we have seen that the damage spreading has also always the in absorbing state, the state in which zeta, which is the difference, is equal to 0, it means x equal to y. If they happen to be all the same, they always stay the same because the evolution now is the same. And so the zeta I equal to 0 is an absorbing state. And a researcher, Peter Grasberg, conjectured that all interaction that have local interaction and one dominating absorbing state, or at least asymmetric absorbing state, I mean, we shall see in the BBR model what it happens, that they belong to the direct percolation universality class. While if the absorbing state is not stable means that if you make an infinitesimal perturbation, not a finite one like in cellular automata, it can break down. Then, and we shall see in a moment, this happens, for instance, if you use continuous system, not for cellular automata, or maybe cellular automata with a very large number of states. Then you have another different behavior, which is called the multiplicative noise. While if you have many symmetric absorbing states, you have still another universality class, which is called the parity conservation. And clearly in the BBR model, this point is a parity conservation, while these two lines are in the directed percolation universality class. And in the Domani-Kinsel, this is essentially parity conservation, and this, but actually this is another universality class due to the other problems. And this is a directed percolation. And okay, so in order to clarify all these differences, we can try to develop a common language. It means that instead of considering a system composed by 1 and 0, suppose that we are taking a certain distance, certain length, say L, and you replace this with a continuous value phi. Clearly, when L is large, but not infinite. And so if you do this, instead of having this 0, 1, 0, 1, 1, 0, 1, 1, 0, so a curve like this, you have something which is smooth, and so you can assume that you can write down a kind of a continuous equation, field equation. And and as usual in this kind of approach, you are trying to relate how this phi behaves in time with some so local process and interactions with the rest of the system. Since you may have fluctuations also inside a given portion that you represent with a single number, you have to introduce also a noise in order to reproduce this fluctuation. You don't know actually how they are. You know from the Landau approach that you need to have at least two powers. If you want a symmetric system like in the Domani Kinsel one, you may want to have one, and this is a this is not the this is the force, so it is the derivative of the free energy. So for the free energy, you have something that goes from here to here. From the force, you have something that goes from say having something like this to having something that goes like this. So this one is a force, say like this. So this goes in that direction. This is a positive force, and this is a negative one. So you put minus a here in order to have this negative slope, plus say a quadratic term, a cubic term that gives this behavior, because you can have now these things like this, and so if you are far enough, you go like this, and you have this transition from here to here, and so you have a stable state and to an unstable state. If you want to have like in the Domani-Hinds, you have to put here a quadratic term, because essentially you are looking at pushing towards 0 or far away from 0. So you have either this situation or this situation. So this is for pushing towards 0, and this is for pushing away from 0. But these are details. And this represents the fact that clearly, if you have, say, not a strong local dynamics, you go into the, say, uniform state. So this is a kind of surface tension that tends to make the system flat. And this is the noise, which can depend or not on the phi. We may have essentially three situations. This constant, and then in this case, the dominant part is the diffusion, and you have in an homogeneous state, essentially easing state, where the final state is a homogeneous one. Or it may be proportional to the square root of phi, so that the fluctuation, which is the square of this, is order phi, and the two terms are all terms are say essentially relevant, and this can be shown that is the case of directed percolation. Or we may have it proportional to phi, and this is the case of multiplicative noise, and we can show by making a transformation that this equation with multiplicative noise can be converted into this one, which is of the, in physics it is called the Kardar-Parisi-Zhang equation, that describes the growth of a surface, for instance, because there is some deposition. And the idea is that for the moment, without this one, if you have the Kata-Parisen-Zhang, then there are a term in which dominates diffusion, and which tends to give you a smooth surface. But if this square of the gradient dominates, then it becomes rougher and rougher at each time. It is like when you have absorption, but it tends to absorb more on the peaks than on the valleys, so the peaks becomes higher and higher, and the valleys are never populated. This term represents a wall, essentially, a term that is a wall that is moving, so all the surface which is pushed toward the wall. And so the multiplicative noise is essentially correspond to the Kata-Parisen-Zhang with this wall domain in different cases. And so this is an idea of giving a different scenario and maybe a unifying scenario of this kind of equation. This is called a Langevin equation, essentially, in physics. Okay, another interesting point which has a lot to do with damage spreading is the opposite of damage spreading. It is a synchronization. So let's start with the maps. So now X and Y are, say, continuous number from 0 to 1, say, for instance, the logistic map, X, 1 minus X, or something like this. And you push with a force, say, P, Y into X. You see that if P is equal to 0, then this is not present, and this is not present, and so essentially you have two independent maps. If the map is chaotic, they diverge. But if P is equal to 1, now this disappears, this is equal, and so X, Y are equal, X is equal to Y in just one step. So there is a critical value of P for which the distance between X and Y goes to 0. And you may wonder how it is, how this is related to other dynamical properties. The idea is that if you compute the distance, this one, then you develop Y around X, so near the synchronization transition, you find that f of Y is similar to f of X times 1 plus times minus X times f prime of X. And so you get this one. So if you start from delta 0, you have to multiply all these terms. You can take clearly the exponential in order to have a logarithm. And you see that these things appears. And this is essentially the Lyapunov exponent of the map. And so if this is greater than 1, we have greater than 0, we have an exponential growth, at least for small time intervals of the difference. If this is less than 0, but here again there is another parenthesis. I've lost all parentheses here. If this is less than 0, you have a convergence to 0. And so essentially you see that the critical property, the critical synchronization transition is related to the largest, to the Lyapunov exponent, or to the largest Lyapunov exponent, if these are high-dimensional systems. And so synchronization is a way of measuring the chaoticity, the Lyapunov exponent, not by studying how things diverge, but how things converge or are pushed one against the other. And in the next lesson, we shall see how this applies to cellular automata. But for the moment, let's continue with maps. And now consider coupled maps. So essentially you have a lattice, like the ones of cellular automata. You perform a kind of, say, spatial coupling. Normally, this is a kind of diffusion. And then you apply a map, and again, you apply a kind, say, for instance, diffusion, and then a map, and so on and so on. And clearly, this system can do a lot of different behavior, can follow a lot of different behavior. Now, if you push, now consider you have a master and a slave. And so if you push every slave towards the master with the same probability P, this analysis still holds, and you find that the critical value of P is related to the maximum Lyapunov exponent of the maps. But this is not really related to spatial chaos, because consider, for instance, that the coupling is a generalized diffusion. So there is a parameter epsilon, and if epsilon is equal to 0, there is no diffusion at all. If epsilon is equal to 1/3, you have the full diffusion, 1/3, 1/3, 1/3. If epsilon is greater than 1/3, you have that the neighboring sites are more influent than the central one. Now, if you compute the Lyapunov exponent as function of epsilon, at least for small epsilon, this decreases. So, because the diffusion decreases the divergence, not spatial, in the tangent space, divergence of the difference. I mean, suppose that you have uncoupled maps, then you have a certain Lyapunov exponent related to each map. If you add some diffusion, the diffusion makes that the difference here cannot completely spread, because it has also to pass something to the neighbors. And so the total spreading is less than spreading, I mean difference computed over all sides, is less than one could have having only local coupling. But in this case, you have no spatial diffusion. So if you are considering when a given perturbation here can spread to neighboring sites, this happens for sure for epsilon greater than 0. So clearly you can define co-moving Lyapunov exponents and something like this, but the idea is that just considering the maximum Lyapunov exponent says little about the capacity of certain perturbation to spread over the system. But we can have a different kind of synchronization mechanism, which is also applicable to cellular automata, which you cannot push simply by tuning the map. In this one, you choose a fraction P of sites, and you synchronize completely this fraction while leaving all the rest alone. And you change in the next time step, you find, say, another fraction of sites, which could be the same or others. And then you synchronize this and you leave the others alone, and so on. So essentially, if you look now at how sites that are not synchronized, because only a single defect here is completely killed in one step. Here, can propagate one step, but then cannot propagate here, cannot propagate here, and maybe here, yes, it cannot propagate here, cannot propagate here because they are synchronized. So you see that a single defect can only diffuse on the percolation cluster that we have already seen in the previous lessons. And so clearly, if you have P greater than the critical value for percolation, it means that there is no percolating cluster, clearly the defect is surely killed. So what is important to study the diffusion on the defect on the critical percolation cluster. And the critical percolation cluster, which is the cluster that goes up to infinity, it is not done with just a single path, but you can see that there are several paths even in the critical percolation cluster. And this is important because the amplification of an initial defect is different if it goes only through one path, or if it has two different paths. And here the defect may also interfere and destroy. They can do several things depending on how the map behaves. But for small defect, they sum over here. So having a lot of branches means that the defects can grow, while having a single branch means that it has to survive on just one step. And okay, so what happens to maps, not to cellular automata, on this kind of clusters? Well, depends if the chaos is able to survive only on a single or a very few paths, or it needs to have a lot of contribution in order to survive. So, and this discriminates a kind of a weak and strong chaos. If you have strong chaos, then the total number of sites which arrive to infinity is essentially all these. So the transition is of the kind of directed percolation, and they only synchronize when the percolation cluster disappears. While if you have a weak chaos, you need to have more paths. So what happens is that the damage survives until the number of paths of converging paths is less than a given number, and then suddenly goes to zero. So we have essentially a first order phase transition in this difference. And now, if you use some kind of map, for instance, Bernoulli shift, generalized tent map, or also logistic maps or other kind of maps, and if you plot the survival damage, say, with respect to epsilon, so I mean, this epsilon, remember that 1/3 is corresponds to the maximum diffusion. This corresponds, so 0 corresponds to no diffusion at all, and 1 or 0.5, depends on how it is defined, corresponds to the maximum diffusion from neighbors, but no diffusion from the center. And you see that this is the line for which, so then the experimental point and the line for which there is a transition from, say, no, this is not, this is a parameter, say, A, the parameter that determines the chaoticity of the system. And this is the lambda, so the, how I called it, the xi or the key. Key is the number of defects. Xi is the size, the, the sum of all defects, but they're essentially similar. And so this is this different from zero, T of C different from zero, and this is the synchronized region. And you see that actually the non-synchronized state survives for small values of A, so for low chaoticity. Essentially, lambda is a log of A. The Lyapunov exponent is a log of this slope. For when the coupling is near to the 1/3. So it means that the actual, say, spreading of damage for coupled maps is more effective the more, say, democratic coupling is, and less effective both for no diffusion, which corresponds to the largest Lyapunov exponent, or neither for the opposite case when you have diffusion but only on neighboring sides. And so another different complementary aspect is the opposite. You can find continuous system, and this is another kind of generalization of a Bernoulli shift. This is a continuous map, which, however, when you simulate this, it has if I remember well, it has a period 3 cycle like this. And if you couple now this equation, these maps, you get a pattern like this, which has some resemblance with those of cellular automata. What is interesting is that these coupled maps are not chaotic. They have a Lyapunov exponent which is different from zero. But if you make a finite perturbation, so an infinitesimal perturbation is reabsorbed, essentially because they are periodic maps. So if you perform a small modification, they come back to the same cycle. But if you make a large enough perturbation so that it changes, in some sense, the phase during this limit cycle, this can spread to all the lattice. And again, you can study this kind of behavior using the master-slave synchronization as before, in order to somehow to define a kind of, say, Lyapunov exponent for finite perturbation. We shall see that we can define it also in another way in the next lesson. And if you want to be extreme, you can use this kind of map, which is defined here. And you see that this kind of map for A, say, large enough, it is this one. And actually, this is a stable map because these zero slopes makes the system, if it is near here, goes, you see, no? If you start from here, you go quickly here. If you start from here, you go quickly here, and you stay there, and so on. So essentially, locally, it goes either to 0 or to 1. But now, if you couple them with, say, 1/3, 1/3, 1/3, you see that if the two are ones, the sum over 3 of the 3 divided by 3 goes 1 again, so it stays here. If only 1 is 1, the sum of the 3 is 1/3, so it gives you again 1. If there are two ones, the sum is 2/3 and goes to 0. And if there are 3 0, you stay in 0. So essentially, once that the system has arrived to the absorbing, say, local absorbing state 0, 1, then it behaves like a cellular automata rule 150, which is, in some sense, chaotic, not from the point of view of Lyapunov exponent, because these are stable maps. The derivative is always 0 in the asymptotic state, so the Lyapunov exponent is minus infinity. But from the point of view of a finite perturbation, it shows spreading, and clearly also in the sense of pinching synchronization. You have to pinch a lot of sites in order to synchronize the system. And what is interesting, and I almost finished, is that if now you study how the synchronization behaves in the, clearly, in another word, if A is equal to 1, it becomes like a tent map and becomes truly chaotic. Still, the synchronized state is can be, if you pinch enough, you can manage to synchronize, but it is a case of strong chaos. And now what is interesting here is that if you now look at how you have to synchronize them using pinching, or how a finite perturbation expands, you find different, these are the critical exponents of the system, and this is the direct percolation critical exponent, clearly when you are in the stable state, and this behaves like rule 150, because here the absorbing state is stable. I mean, an infinitesimal perturbation here of an absorbing state, which is composed of zeros and ones, is reabsorbed, while here, which corresponds to, say, large enough A, you have the multiplicative noise of Kada-Parisi-Zhang equations. And so they are both examples of strong chaos. Actually, you see that A is always greater than 1. But you can have a different kind of, say, behavior passing from direct percolation to Kada-Parisi-Zhang. Finally, we have seen that the mean field corresponds to shuffling the system in each time step, which is essentially the same as instead of having local coupling, you choose at random. So in the local coupling, this one depends on these three. But you can, if you assume that this chooses 3 neighbors at random at each time step, you have the situation of mean field. Now, there is another possibility. It is of having quenched the connection. So you start from a regular one. You rewire a certain fraction p of links, but then you keep them in this condition, not rewiring at each time step. And now, what is interesting is that when p is essentially large enough, or essentially 1, you have again the mean field transition, the mean field behavior. But this can be interesting because if we take the BBR model, we have seen that it is a totalistic automata. 0, 0, 0 goes into 0, 0, 0, 1, etc. goes into 1 with probability p, etc., etc. Now, if you consider the case q larger, p larger than q, it is a kind of, say, anticonformistic way, because the probability of having 1 is larger if you are surrounded by more zeros than if you are surrounded by more ones. But still you have the absorbing state. We can generalize this to a totalistic model with, say, this is the local field, so H is the sum of the sites in the neighborhood. And when the probability, this is the probability of having 1 given H, when the probability It's like here you have an anticonformistic behavior. You can also eliminate, if you want, the absorbing state by putting something like this, or simply putting something here which is not neither 0 nor 1. So we don't have absorbing state now. And if you compute the mean field equation, you find something like this. And so you remember, now this is the probability of having 1 at time t plus 1, and given the probability of having 1 at time t. These are for different values of some parameter j. And what happens is that these curves can be either stable, for instance, or chaotic. If you take this, it can be chaotic. So what happens is that you have a system which, in the mean field case, which should correspond also to the case in which you have a random quenched connection, is chaotic. But from the microscopic point of view, if you perform the simulation, you find essentially C equal to 1/2, because clearly the system is chaotic at the mean field, but since there is no spatial correlation along the system, each patch evolves by itself. So everyone can say fluctuate, and the total sum of this fluctuation gives you an intermediate value of C. So these are for the mean field map. For the mean field map, changing the parameter J, you see that you have essentially a bifurcation diagram similar to that of the logistic map. You pass from a stable state at 1/2 to a period 1, then period doubling. Actually, this is some particular case, but you have a period doubling, and then you have chaos with the periodic windows, and so on. This is for the mean field map. Now, what happens if you change the rewiring of your system is that you have a very something that is very reminiscent of but you work here with the J fixed. And what happens is that these are the mean field equations. When you have regular lattice, the superposition of uncorrelated oscillation in several piece of your system gives essentially 1/2. When you start rewiring, you start to have correlations, spatial correlations in the system, and the system tend to synchronize, this time in the sense of being the same on all the lattice, and so they start to oscillate coherently. And so finally, when you have very large rewiring, so this is P equal to 1, this is P equal to 0, you have actually exactly the mean field equation. So you observe this kind of behavior, for example, or this kind, depends on the value of J, and this is exactly here. And this is an interesting also effect in a phase transition induced by a change of the topology of the connection, which is also things that has been rarely studied. Okay, I think that for today this is enough. Are there questions, comments? Okay, if not, we can see again Friday. I think that Friday I have to run a bit in order to give you at least a glimpse of the rest of the things that actually it is. I have not calculated well the length of my exposition, but what we can do, and then we do, and then the rest we leave. Okay, so I can stop the recording.